This is Frank. Frank is my BB unit droid from the Droid Depot at Galaxy's Edge. And Frank has been through a few things. I used Frank to figure out how personality chips worked. And then I used Frank to try my own personality chips. Then I started working on figuring out how Frank thinks, because he developed a little bit of a problem with his brain. And I'm not sure what was going on here, but Frank was having a bad day. So this is Frank's core. This is the main logic board. On the left here we have a Bluetooth microcontroller that is responsible for handling communications with the remote control. On the bottom right there are a couple of chips here. Each one controls one of the two motors in Frank, or really in any other BB unit droid. There's a couple of these rectangular chips here in the middle of the board. Those are voltage regulators. They take a voltage that's some value and drop it down to, well, in this case you can sort of see the numbers 5 and 0 after it. This creates 5 volts from whatever the battery voltage is. And then there's another one over here that creates 3.3 volts. The 3.3 volts is used to power the Bluetooth microcontroller and the audio microcontroller that is on the other side of the board. Here's the other side of the board. There is a big blob of epoxy underneath which is the audio microcontroller. There's no need for me to try and remove that epoxy to see what it is, because I can tell you it is a General Plus GPCD9T. And the reason I know that is because in our unit droids, their logic boards have the model number of the chip printed on it, which was very helpful. So when I first got Frank, I tried to figure out how Frank worked, and I started looking at this logic board, and you could figure out a few things. Again, the motor, the Bluetooth controls, the connections to the motor and batteries. Up at the top here, that yellow connector goes to a coil of wire that pulses, and those pulses get picked up by another coil of wire in the head to make the LEDs blink. These yellow wires go off to the speaker. This rainbow connection over here, that goes off to the personality chip socket. And then the last few wires with this brown connector here, those go off to the LED and button that are used to pair your droid with your controller. On the back here, we have power coming in from the left-hand side. There's a little plus symbol there to let you know. This big rectangular thing marked PTC1, that's a thermistor. Its resistance will increase as more current flows through it, as more electricity goes through it. It's essentially like a fuse. It will cut off electricity if too much is getting into the circuit. But one thing that's confused me is this circuit on the bottom right here. And I tried to figure out what it was for by sketching it out in a notepad. And here's part of that sketch. And you can see the voltage, or the power, the electricity from the battery, marked as VBAT here, is coming into this circuit. And there's a transistor here, and there's a second transistor here, and you can see it goes off to these little boxy looking things with an arrow on one end, which represent connections to the microcontroller. So you can see it's going off to 3 different pins on the microcontroller, and there's a couple of transistors, and what does this all do? I don't know. Why did I write beefy over here? That's who knows. But long after I sketched that out and then forgot about it, I saw this. This is part of a schematic of an R-Unit droid that was created by Sedacious on the Galaxy's Edge Discord server. And the section we're looking at right now is the same section that I had sketched out earlier. There we've got a transistor here, a transistor here. It's going off to a microcontroller. Here's another line going off to the microcontroller. You can see what's marked here is 9 volts in. That's that VBAT in my schematic that connects to the battery. But the schematic that I'm going to use to really analyze this circuit is this one. And this schematic comes from Russ from the Galaxy's Edge Discord server. And he, like Sedacious, did a full, drew out a full schematic of his BB unit droid. And Russ has correctly indicated exactly what the circuit is for by labeling this section the battery level monitor. This circuit is responsible for allowing the droid to detect the battery voltage. And if the voltage from the battery pack drops below a certain level, the microcontroller will shut the whole system off. Now, while this schematic is for a BB unit, Sid's schematic is for an R unit droid, but you're going to see they're pretty much the exact same thing. We have a transistor here marked Q5, which is connected to the base of the other transistor. We have this transistor here connected to the base of another transistor. We can see that there is this 100K pull-up resistor connecting the base of this transistor on the right to 9 volts. Here's that 100K resistor connected to 9 volts. We can see the collector of this transistor goes off to this 300K and 47K, and we're going to find out that that 300K resistor is a mistake in Russ's schematic. But let's go take a look at Sid's. There's your 300K resistor, your 47K resistor, and what's really just a 100 ohm resistor that then goes off to the microcontroller, that Bluetooth microcontroller. So the point is that all three of these schematics are the same. And this schematic is the same for an R unit droid as it is for a BP unit droid. So let's analyze this schematic. And I'll try to go quickly, but I also want you to sort of understand what's going on here, so bear with me. So Q5 and Q4, those are transistors. You can think of transistors as electrical switches. When the transistor turns on, the collector and emitter, which are marked by C and E, will be connected together. And when the switch is off, they are not connected. To turn a transistor on, electricity needs to be able to flow between the base, marked by a B here, and the emitter, and that electricity must be able to flow in the direction of the arrow that you see on the emitter. So in this case, this transistor over here, electricity needs to be able to flow from the base to the emitter. Now the emitter is connected to ground, which is going to be at 0 volts, you can think of it. The base of the transistor here is connected to a microcontroller pin, and that microcontroller is going to be outputting either a high voltage or a low voltage. Low voltage will be 0 volts. High voltage in this case is going to be 3.3 volts. So if we have 3.3 volts here, and if we have 0 volts here, we have electricity that can flow from the base to the emitter through that in the direction of the arrow, turning this transistor on. So the point of this is that the microcontroller can turn this transistor on or off. When this pin is not high, you can see this 100K resistor here, marked R30, is connecting that base to ground. Since this is 0 volts and this is 0 volts, there's no electricity that can flow from the base to the emitter, so the transistor is off. So unless the microcontroller is outputting a high signal or a high voltage on that pin, this transistor stays off. Now, if we look at the other transistor here, you can see the arrow is pointing in a different direction. Arrow is showing that electricity must be able to flow from the emitter to the base. So if we look at the emitter and we follow it back here, we can see it's connected to what Russ has marked here as 9 volts. You can also think of that as that's the battery power supply. So we have 9 volts on the emitter. In the base, ignore this branch coming off of it for a moment and just look at the resistor that's connected to the base here. We have a 100K resistor that is connected between the base and 9 volts. So that means that the base will have 9 volts, the emitter will have 9 volts. This transistor is going to be off because no electricity can flow from the emitter to the base. The difference in voltage between the two is the same. There's no voltage difference, so there's no push in one direction or the other for electricity to flow. Now, if we turn on the other transistor, which connects this collector to ground here through the emitter, right? These two become connected when the transistor turns on. You're pulling the collector to ground, which means you're pulling the base to ground because the collector is connected to the base through this 10 kilo ohm resistor. So where is the 9 volts going? That's coming from this 9 volt supply and going through this resistor. That 9 volts is going to ground. It is, because it's 100 kilo ohms, it's only allowing a very tiny amount of electricity through it. And as a result, this 10 kilo ohm resistor will allow more electricity through it. So all of the tiny little trickle coming through this 100K resistor is going out through this 10K resistor down to ground. It's not going into the base. We just need to focus on the fact that when this transistor turns on, it pulls the base to ground. If the base is connected to ground, then electricity can flow from the emitter to base. That's electricity is flowing in the direction of the arrow, turning on the transistor marked Q4. So by setting this pin high on the microcontroller, this transistor turns on, which in turn will turn this transistor on. Setting the pin at the microcontroller to high turns Q4 on. That's where we want to be at right now when we're looking at this schematic. So if this transistor is on, the emitter and collector are connected together. So that means that 9 volts is coming through the emitter and out the collector into what's left of this circuit here on the right-hand side. The circuit on the right-hand side goes off to another pin on the microcontroller. In essence, the microcontroller now has the opportunity to taste the voltage coming from the battery. But why not just connect the battery directly to the microcontroller? There's a reason for that. This microcontroller is rated to operate at 3.3 volts. Its internal circuitry is meant to operate at no more than 3.3 volts. You feed it 9 volts and it's not going to like that. So you need a way to take that 9 volts from the battery and bring it down to a level that the microcontroller can use and it won't damage the microcontroller. Enter a very common piece of circuitry, the voltage divider. R23, which is marked as 300 kilo ohms, and R25, which is marked at 47 kilo ohms, form a voltage divider. So 9 volts comes into this circuit here, and at this point, between R25 and R23, the voltage is going to be something less than the 9 volts. It's being divided. Now, if both resistors were at 300K, you would have half of whatever the voltage coming in is. So you would have 4.5 volts instead of 9 volts here. In this instance, though, the difference between the two is greater than that. Electricity coming into this point, most of it's going to go out through this lower value R25 resistor to ground. So the voltage here is going to be less than half. Now there's a formula for this to figure out what voltage exactly is going to be there at this point between these two resistors. And we'll get to that in a second. I just want to cover a couple other things in the schematic. C31 is a capacitor. That's there just to sort of help stabilize the voltage. It acts like a little reservoir of electricity. So it fills up, and then any tiny little fluctuations in the electricity coming into this part of the circuit, it can smooth that out. If there's a tiny little dip, it can let a little electricity out to keep the level of electricity smooth. If a bunch of electricity comes in, it can sort of start storing it up and dump it back out when it needs to. It helps keep a nice level of voltage through this part of the circuit. Because otherwise, if you had, relatively large spikes of voltage going through here, then your droid might start turning itself off when the battery voltage actually isn't that low. But because there's a little dip in voltage here without that capacitor, your droid's going to think, oh, I went below the magic voltage level, I'm going to shut down. So that capacitor plays an important role here. And then R21 here, you can see it's marked as 300K. In reality, as we saw on the SID schematic here, it is really a 100 ohm resistor. That is there just to cut down on the flow of electricity going into the microcontroller a little bit. R23 here, which is set at 300K, is going to do most of that work, but the microcontroller doesn't really need to consume a lot of electricity. It just wants to see the voltage level, so that resistor is there to sort of help that out. Not let too much electricity go into the microcontroller. Okay, so a resistor voltage divider. Let's take a look at the formula and figure out what voltage is actually getting into the droid. And let's see if we can figure out what voltage the droid decides to turn off. So the formula here is the voltage coming out of that divider equals to the voltage coming in times the value of the second resistor divided by the first and second resistor added together. So what is R1 and what is R2? Well, electricity is first coming through this 300K resistor. That's the first resistor in the divider. That is R1. The second resistor will be R2, or the second resistor marked as R2 will be this one, 47K resistor here. So we know what R1 and R2 are. If we have a voltage input of 9 volts, we can see the voltage coming out is going to be about 1.22 volts. If we have a voltage of 7 volts coming in from the battery pack, we can see the output of that voltage divider will be about 0.95 volts. And if you remember from the previous video I did looking at when you need to replace the batteries in your droid, when I was feeding it about 7 volts, it was shutting down. So my educated guess here is that the droid is going to power off if it sees a value below 1 volt on that pin. So if we go back to that schematic, here's on the far right hand side, that is the pin going into the microcontroller. We have our voltage divider of 300K and 47K going off into the microcontroller. If the voltage going into the microcontroller is under a volt, the microcontroller shuts down. If it's over a volt, the microcontroller is happy, the droid keeps operating. So can we change one of those resistors and thus change the voltage divider such that when a lower voltage is coming in, the voltage divider will output something at or above 1 volt? Either R1 or R2 could be changed. I have opted to focus on changing R2, resistor 2, which is that 47K resistor. I've reworked the formula here, solving for R2. And so if we assume a voltage coming in from the battery pack of, say, 5 volts, which at that point the batteries in that battery pack are really, really dead. But If we focus on trying to do 5 volts coming in, and we want the voltage out of that, going out of that voltage divider to be 1 volt, meaning the droid will happily keep operating even at that voltage level, and we assume R1 is staying the same at 300K, what is R2? Well, let's plug these values into the formula, and we come up with 75 kiloohms. So the current resistor there is 47 kiloohms. If I increase that value, I will get a droid. I should get a droid that's going to keep operating at even lower voltages than what it operates at now. Now I have a pack of different resistors of different values, but I don't have a 75K resistor. The closest values I have are 68K and 85K. So what should I use? Well, let's rearrange that formula one more time. This time I want to figure out, given that I want a voltage out of 1 volt, and I know that I have a R1 of 300K and R2, I'm going to change it. I'm going to try both the 68K and the 85K values. What's that minimum voltage that's that I need to get that 1 volt coming out of it? So here are my values. Plug it into the formula, and with a 68K resistor, the voltage the incoming power needs to be before it will turn off is 5.4 volts, but if I use the 85K resistor, the droid will keep operating at even 4.5 volts. So which should I go with? There's another layer here that should be covered real quick, which is, earlier I talked about the voltage regulators, and I pointed out there's a 5 volt voltage regulator. And those types of voltage regulators, they preferred if the input voltage is higher than the output voltage. So in this case, 4.5 volts would be a bit lower than the 5 volt output that voltage regulator wants to output. Now, I could run the droid at 4.5 volts, but what's going to happen is that voltage regulator is essentially going to always be on. It's going to act as not a short, but sort of like a diode. There's going to be a little bit of a voltage drop, but it'll still spit out 4.5 volts, or in this case, it'll probably be about 4.2 volts, 4.3 volts maybe. But also it means that the voltage regulator is always on. It's operating more as a resistor at this point. It might heat up a bit. You know what? I think I want to go with the 68K version. If you are in a position where you want that 4.5 volts or even something lower than that, I would then look at removing that voltage regulator completely and replacing it with either just a jumper or probably some kind of Schottky diode, some diode that has a very low forward voltage. So the plan now is to find this R25 on the board and remove it and replace it with a 68 kiloohm version. So here we are back at the board. And let's see if we can find where R25 is. Now, I know it's in the lower right-hand section, and if we look around here, we can see it right here. You can see the marking on the resistor too. It says 473. That's 4, 7, and then 3 zeros after it, or 47 kiloohms. Earlier, you noticed in Russ's schematic, he had written down one of those resistors as being a 300 kiloohm resistor. Well, if we look at Russ's schematic, we can see R21 here, which he's listed as 300K. Let's see if we can find R21 on the board. R21 is, I don't know if you can see that, it's right here in the middle. And right next to where it says R21, we see a resistor that says 101. So that's 10 followed by 10, a 100 ohm resistor. But you also see on the markings on the PCB here another thing that says R16. So that's pointing to another resistor called resistor 16. And what I think happened here is Russ saw this R21 And he thought it was this resistor next to it. It says 304, that's 30, and then 4 zeros after it, or 300K. But I think R16 is actually referring to this 0 ohm resistor. And R34 is referring to this 100 ohm resistor. C20 is referring to this unpopulated thing here, which might have been a capacitor. So I think R21 is this 100 ohm resistor, and looking at the board, Russ just read this one wrong. So no worries. There's our resistor. That is what I need to change. So, enough of this slideshow business. It's time to break out Frank. Open it up and replace that resistor. But before we do that, there is one other thing I just want to mention here real quick. I'll get it out of the way before we get to the meat and potatoes of this video. This mod isn't really going to get you anything extra out of your batteries. If your battery pack is at 7 volts and you have 6 AA batteries in there, that means that each battery on average is operating at about 1 volt, which is considered dead for most applications. So at that voltage level, the batteries are on their last legs. They're not able to produce the kind of current you need to drive the motors. The designers of these droids chose 7 volts as the cutoff voltage for a very good reason. There's really no reason at all to apply this mod that I'm about to do. I mean, this mod, it's just an experiment. And, well, some experiments don't go so well. So, this is more for informational purposes, and I definitely recommend that this is not something you do. End of speech. Let's crack open Frank. Okay, here we go. Let's head off to the side. Crack Frank open. There is the part that we care about. First up, let us remove the bottom half of the shell. Okay. Remove the board. Disconnect everything here. Some of these connectors are definitely going to be a little tight. Be patient. Be very patient. Okay, so there is the board. And I need to grab R25, which is right there, clearly marked 473. Okay. I am going to put that in a vise and get set up. I just want to remove that one resistor, R25, and I suppose I could just hot air the whole thing, but because it's a daughter board, well, for the audio controller here and the Bluetooth controller on the other side, I'm worried about those coming apart as well. So I really just want to go for the one resistor with my soldering iron here. So I think I'll just start going at it and, I don't know, play it by ear, I guess. I'll pre-tin this side first. And I'll try and pre-tin the other side here. The camera's in the way. All right. So what I'm doing is I'm trying to sort of dilute what's almost certainly lead-free solder, which is going to have a higher melting point than regular solder. And it also doesn't flow as well than the leaded solder that I'm using here. So I'm sort of diluting that lead-free solder a little bit. And by the fresh solder also will have flux to help things along. But what I plan to do here is get a good blob of solder on either side and then heat them both up at the same time with the iron. And that should get things loose. Alternatively, I might try and just blob the iron and then go back and forth like this. There we go. I think that's done it. And now I need to clean those pads. And I'm going to do that with a little bit of this copper braid stuff that has a little bit of flux in it. It will wick the solder up into the braid away from the board, removing the solder. So you can see I've got the braid here. I'm holding it in the tweezers. I've given it a twist and I've bent it at the bottom so it should hopefully fit in between the other components on either side of where the resistor was. Just sort of put my iron in there, gently scrape across, and there we go. We've got clean pads. Excellent. Okay. Now, next step is to find the replacement resistor. I've got a resistor book here. Let me zoom out and maybe you can see that. My book of many resistors. And I think I'll show you. See, I have a 68K or an 82K. I don't have the 75K that I was looking for. And I believe I decided to go with 68, right? Which is going to give me 5.4 volts of minimum operating voltage. Cut that out like that. Now you can see that these are 0603 resistors. I'm just going to do a quick comparison here and see if the size matches up with what I pulled from the board, and that you can't see. Let me put these on my finger. This will help a little bit. Just because I didn't confirm ahead of time what the size was going to be. So you can see that says 683 on the new resistor. That's 68 and then 3 zeros after it. 473 is the old one. 47 followed by 3 zeros. So it's a 68K resistor I'm putting on there. So I need to free this from the plastic cover of the whatever they call this. There. Okay, so I'm just going to put that off to the side so I can have a chance at losing it. Okay, so step one is to pre-tin one of the pads. Now it looks like this is right, this is to ground. The big ground plane is on the left here, and on the right goes to the, well, there's one of those are the two transistors that we talked about in the schematic. So I'm going to pre-tin the pad that isn't connected to ground because that won't require as much heat, like so. And now I'm going to bring in that resistor carefully. And reflow that blob of solder. Trying to get the resistor to catch on to it, while also not knocking the camera. Alright, that looks pretty good. I'm going to push down with my tweezers ever so slightly. Reflow the solder one more time just to make sure that resistor is flat. That looks good. Flip the board around here. Again, when you're soldering this stuff, especially when it's tiny components, reorient the board so it's more comfortable or as comfortable as it can be for you. Don't feel like you're stuck in one position once you start soldering. All right. Let's take a look. There's probably a little too much solder there, but that's fine. It's not going to impact anything. It just makes it more obvious to anybody else who comes across this board later that it's been messed with. However, there are other clues, such as the motor driver that clearly has been replaced, or the extra connector here, which is not populated on a stock board. All right, enough of this. You want to do what I want to do, which is put this thing back into Frank and hook it up and see what kind of voltage it'll take or it'll operate at before it turns off. So let's see if my interpretation of that schematic was correct. I have these two wires coming out to the side here. Those I can find the ends of my bench power supply probes here. Just clip that on like so for positive and negative. And we're pretty much ready to give this a go. Okay, is everybody ready? Is everything in shot? Let's see what happens. Now, hopefully nothing happens except it'll turn on and start making noises. I have to... There we go. Okay, we're powered on. Take this opportunity to use one of my fancy new tall version of the personality chip. Okay, so everything's working, so now it's time to start stepping down the voltage. There we go, 7.5 volts. Still working. I expect when the voltage drops below the threshold and the microcontroller decides to shut everything down, there should be a sound that plays without me touching the remote. So I'm just going to leave the remote over there. All right, here we go. We are going down to 6.5 volts. This should turn it off under normal conditions, but now that we've modified it, it should stay on. Still on. That's a good sign. Okay, so now I am going to go down to 6 volts. 6 volts. And you probably don't believe me, of course. Which, you know, I respect. So let me hook up a multimeter here. Where do I want to put that? That can go off to here for the moment. There's the multimeter on volts. Just hook this up like so. Like so. There you go. You can see we're at 6 volts. Now I'll just leave my remote way over here so you can see I'm not pressing anything. Okay. Let's go down. Now, if the math is right, this should turn off at around 5.4 volts. So let's go. .75 volts. Still running. All right, we're getting close now. 5.5 volts. Still operating. Okay, here we go. Where will it turn off? We're close. .4 volts. It's still alive, but not for long. Here we go. Let's see. Now, the reason it's not shutting off right at 5.4 volts is because the resistors will have they're not precise. They're like 10% or 5% out of their value. So, 47K resistor is going to be off by about maybe 407, or in this case, a 68K resistor would be out by like, 680 ohms. So that will impact the voltage. So it could have been higher. It looks like the cutoff is going to be a little bit lower. Oops, going the wrong way. 5.3. There we go. It just shut off. It just shut off at about 5.28 volts. Not bad. Not bad at all. The math sort of works out. It's almost like I know what I'm talking about. Turning it back on now. Let's do that again. $5.35. 5.3 volts is when it's cutting out. So I bring it up to 532. We're on. Drop it. Oh, there we go. It shut itself off. Probably fluctuations. Remember, I talked about the capacitor that's in parallel with that the resistor that we just replaced. Still, larger voltage spikes from maybe driving the speaker in the system are just enough to throw it off and shut it down. Certainly, if this was hooked up to the motors would be a huge current draw and drive that voltage down, and also could trigger that cutoff. All right. And it shuts itself off. So 5.33 volts, it looks like, is where it stops working, where it will shut itself off. Cool. That was a nice little experiment, one that proved that would work. Now, I think I've already covered this in my big long speech at the beginning here with the slideshow, but why didn't the designers allow your batteries to drain more, to suck the last bit of juice out of those batteries? And it's because the chemistry in those batteries, as the batteries get lower in voltage, it can't react fast enough. It can't produce the current that it needs to drive the motors. So that's why they have this thing shut off when it detects the voltage go below 7 volts from the battery pack. That's it. That's all. That was interesting. I'm glad this worked. I'm glad my math worked. I was a little nervous there. Have fun.